Welcome to the last lecture of this week. In the last lecture, in the second lecture, we have seen a theorem, and we have not proven and we have not explained the meaning of that theorem. In this last lecture, we are going to do that. So let us remember our theorem. Well, define a square root S of the matrix GQG transpose as S transpose is equal to GQG transpose. Then the theorem statement tells us that if A and S, the pair AS, is reachable, then A is stable if and only if sigma infinity exists. Okay? So now we are wondering about the stationarity of the covariance, sigma infinity, whether sigma k converges to a sigma infinity, which is a positive semi-definite matrix or not. Remember, we have already seen a theorem that says that A is stable, then sigma infinity exists. Okay? But we were looking for a condition which would enable us to say the reverse implication. Okay? And that condition is the reachability condition, and it is related to a matrix and a matrix S that is defined in this implicit form. All right? So here, in this definition, first I need to talk about A. So this define S square root. In general, this square root definition is not unique. So there might be infinitely many S matrices that would satisfy such a condition. But the theorem statement really does not depend on that. For any S that satisfies that statement, the conclusion of the theorem would actually hold. And so here, it is not this square root of GQG transpose, but it is true for any square root. And in general, the square root definition that we use in 501 is not like this. Remember, we define the square root in 501 as any matrix which will satisfy this type of expression. So here, the square root definition that is used by our book is also different than that of 501. Okay? Now we're going to go into the proof of this theorem, but before that I would like to remind you what reachability was, or what were the conditions, and we have also given some facts in the last lecture, and I would like to also mention those facts a little bit before going into the deep proof here. So here we say that AS is reachable. Sorry. The pair AS is reachable if and only if we have given the defining condition here, AS, A to the n minus 1 S has full row rank. This was the defining condition of reachability. And we have given an equivalent condition to this one. It is I from 0 to n minus 1, A to the I. And I have here S transpose A to the I transpose is positive definite. Okay? These are equivalent conditions. And here we see that if this A is A and S, if this pair is stable, since S and S transpose, I have equality of that matrix with GQG transpose. This is equivalent for this theorem that I from 0 to n minus 1, AI GQG transpose A to the I transpose is positive definite. Okay? So here we can say that if AS is reachable, then this matrix is positive definite. If this matrix is positive definite, then AS is reachable. Okay? So we are going to use, and here you really understand why really it doesn't matter which square root of GQG transpose we use. Because whatever square root we use here, it's going to satisfy this equation. And you see that in the theorem, we're only going to need SS transpose, which is GQG transpose. Okay? Whatever square root, whichever square root we choose, that is going to satisfy this equation, and that would enable us to replace SS transpose with GQG transpose in the theorem. Okay? So this was the reachability condition. In this, since I talked about the meaning of reachability in the last lecture really a lot, actually more than a lot, maybe too much, then in this lecture, I will not talk about the meaning of reachability, but when we go into the meaning of this theorem, we are going to talk about the connection between the meaning of reachability and this theorem. And the next thing that I will remind you is that if A has an eigenvalue lambda I, EI, then A transpose has an eigenvalue at lambda I. Okay? And the eigenvector corresponding to that eigenvalue is called Li. So it is Li is the right eigenvector of A transpose belonging to lambda I. Okay? And when I take the transpose of this equation, I get Li transpose A is equal to lambda I Li transpose. And that means that this Li is the left eigenvector of A belonging to lambda I. So here therefore, for any matrix A, if it has an eigenvalue lambda I, it has a right eigenvector for that eigenvalue, and it has a left eigenvector for that eigenvalue. Okay? The right eigenvector is the usual eigenvector that we define, and the left eigenvector is the eigenvector of A transpose belonging to lambda I. All right? So here, let us also talk about the complex eigenvalue case that we have defined. So let us say that here, let me say that this eigenvalue is real. Let us say that lambda I is real. If lambda I is real, there is no possibility that EI can be complex. So if lambda I is real, then EI, the eigenvector, should be real. Okay? Let us say that lambda I and EI are real. In that case, what would happen if I take the complex conjugate of this equation? Nothing should happen, right? So when I take the complex conjugate of this equation, complex conjugate of A is itself A, then EI, complex conjugate, but EI is real, so I have EI conjugate here, and lambda I conjugate, lambda I is real, so lambda I conjugate is itself, then I have EI conjugate here. But since everything is real here, this is equivalent to A times EI is equal to lambda I EI. Okay? The thing actually, another fact appears when lambda I and EI are complex. Okay? I know that when lambda I is complex, then EI is going to be complex. And since A has all real elements, lambda I complex conjugate is also an eigenvector of this eigenvalue. Okay? So sorry, lambda I complex conjugate is also an eigenvalue for the A matrix. So I have A times an eigenvector is going to be lambda I complex conjugate times the eigenvector. Okay? And here in the last lecture we have just shown that the eigenvector corresponding to that eigenvalue is nothing but the complex conjugate of the eigenvector for the original eigenvalue. Okay? We have shown this fact. Okay? So you see that when lambda I and EI are real, this equation is correct. I can just take complex conjugate of everything, and the complex conjugate reduces to the original quantities because of the realness, and then lambda I complex conjugate becomes lambda I. Okay, and in the complex case, I have already this equation. The same is actually correct for the second equation. So if lambda I and Li are real, then this equation is satisfied. A transpose Li complex conjugate is equal to lambda I complex conjugate Li complex conjugate. Okay? So this equation is satisfied. Then Li conjugate is itself, lambda I conjugate is itself, then it gives me the original equation here. And when lambda I and Li are complex, in that case, I know that A transpose is also going to have lambda I conjugate as it is eigenvalue. And the corresponding eigenvector is going to be just Li conjugate. Okay? So you see that this equation is correct when both Li, for both of the cases, when lambda I is real and lambda I is complex, such an equation would be correct. And the similar thing is going to be for the last equation here. And if they are real, then the last equation is going to be Li transpose, complex conjugate transpose, A is going to be lambda I complex conjugate, Li complex conjugate transpose. In this case, complex conjugate transpose is nothing but the Hermitian operator. Okay? So when these eigenvalue and eigenvector are real, this is going to be Li itself, this is going to be lambda I itself, and this is going to be Li itself. Okay? So I will get back the original equation when lambda I is real. But this is nothing but Li Hermitian A is equal to lambda I complex conjugate Li Hermitian. Okay? Because complex conjugate transpose is the Hermitian operator. So you see that here, this equation is correct when lambda I is real. What happens when lambda I is complex? And it is this second case, and so I would have Li Hermitian A is equal to lambda I complex conjugate Li Hermitian in that case as well. Okay? Because if actually A has an eigenvector, if A has a left eigenvector, Li, belonging to lambda I, then A is also going to have an eigenvalue, complex conjugate of lambda I, and the eigenvector corresponding to it would be Li complex conjugate. But in that case, an equation of this form would be satisfied. Okay? So you see that this equation is correct when both lambda I is real and when lambda I is complex. All right? So we're actually going to be using these equations in the proof of the theorem. So now let us go into the proof. So in the proof, of course, we have an if and only if statement here. So an if and only if statement, in order to be able to prove an if and only if statement, you have to prove both of the implications. But remember the earlier theorem that we have seen in this course. The earlier theorem has already proven this implication to the right. We know that if A is stable, then sigma infinity exists. All right? So we already, let us say we have already given a theorem. We have already given a theorem that states A is stable, then sigma infinity exists, and proven it. So there is no need for a proof of the right implication to the right. Okay? So I only need to prove the reverse implication. Okay? So we only need to give the proof for this part. So now let us start to prove. The first thing is I'm going to assume this part. So suppose sigma infinity exists. So I know that the covariance for a linear Gaussian system satisfies this recursion. Sigma k plus 1 is equal to A sigma k, A transpose plus GQ G transpose. Okay? If sigma infinity exists, then I can take the limit of both sides as k goes to infinity. Okay? Take the limit as k goes to infinity, which is going to give to us sigma infinity is equal to A times sigma infinity, A transpose plus GQ G transpose. All right? So now I have a single equation relating sigma infinity to itself. I could write this because I'm assuming this part and I'm trying to prove the implication. I will prove the statement if sigma infinity exists, then A is stable. So here I'm going to set out from this statement, suppose sigma infinity exists, and then I will prove that A is stable. All eigenvalues of A are in the unit circle. Okay? So I have this statement. Now I'm going to do the following manipulation on this. So I have sigma infinity is equal to A times, instead of this sigma infinity, I'm going to substitute the right hand side here, because the right hand side is also sigma infinity. So I will write A sigma infinity A transpose, and I would have, I have plus GQG transpose. This is what sigma infinity is. And I would have A transpose plus GQG transpose. Okay? But this is going to give me the following equation. Sigma infinity is equal to A squared sigma infinity, A squared transpose. This is. And I have A GQG transpose, A transpose plus GQG transpose. Okay? And now I'm going to do the same thing to this one. I will write sigma infinity and A square. Instead of sigma infinity, I will substitute this again. Okay? And that's going to give me, this time, A cube, sigma infinity A cube transpose plus A square GQ G transpose A square transpose plus I would have this A GQ G transpose A transpose plus GQ G transpose. Okay? So you see a trend here. And I will continue this. So you see a summation here of GQG transpose multiplied with A from the left and from the right with A transpose, and then multiplied with A square and GQ A square transpose. So you see that a summation like this is forming on the right. Okay? So let me think that I continued this logic until I continued with this logic n times. Okay? In that case, I would have sigma infinity is equal to, I would have here, this is, so I would have here A to the n, I think, yes. And I would have sigma infinity A to the n transpose. And here I would have I from 0 to n minus 1. You see that when n is 3, these powers of A are continuing until n minus 1. So here I would have A to the I, GQ, G transpose, A to the I transpose. Okay? So this is what this limiting sigma infinity satisfies. Okay? Now, all of our proof, the rest of the proof is going to be based on this equality. Why is that? Because here you see that this matrix is nothing but this reachability matrix. Okay? No, it's not this is the reachability matrix M. Okay? This matrix is sometimes called in control literature as the reachability Gramian, and here we see that this matrix appears on the right. And I know that if A and S is stable, this matrix is positive definite. Okay? I know that this matrix is positive definite because in all of the theorem, we are assuming that A and S is stable and that the equivalent condition for that is this matrix being positive definite. Okay? What can you say about this matrix? This matrix is actually, I know that this is going to be positive semi-definite, and because it's a covariance matrix actually, and that matrix times a matrix and that matrix transpose. So you know that this term is positive semi-definite, so this is larger than or equal to 0, and you know that this term is positive definite. Okay? And when you sum a positive semi-definite matrix and a positive definite matrix, you always end up with a positive definite matrix. Why is that? Let us look at this. X transpose sigma infinity X. I multiply this equation from left-hand side, from the left with X transpose, from the right with X here. Then I do the same here. X transpose sigma infinity, X transpose A to the N, sigma infinity, A to the N transpose, plus here I have this matrix, X transpose, times the summation, which is this positive definite matrix, A to the I transpose times X. This matrix is positive semi-definite, that there is an X here. That means that this quadratic form is always larger than or equal to 0. Okay? And this matrix is positive definite, so when X is non-zero, so this is always larger than 0 for all non-zero X. Okay? So I'm summing a positive constant, a positive number with a non-negative number. The summation of these numbers should be always positive for all non-zero X. Okay? That means that this X transpose sigma infinity X is strictly larger than 0 for all non-zero X. But what does this mean for sigma infinity? Sigma infinity is positive definite. Is positive definite. The theorem doesn't say anything about it, but this is a side product of the assumptions of the theorem. Okay? We have not proven anything about the statement of the theorem, but somehow we have proven that if A and S, this pair is reachable, and if sigma infinity exists, then we have proven that sigma infinity should be positive definite. It cannot actually have 0 eigenvalues. Okay? It has to be positive definite. All of its eigenvalues should be strictly positive. Okay? So sigma infinity is actually invertible. So now let me erase this part. So now we are going to try to prove something related to the actual statement of the theorem. So the statement of the theorem, we need to prove that A is stable. Okay? We set out from the statement sigma infinity exists. As a side product, we have proven that sigma infinity should be positive definite. Now we need to prove A is stable. And for that, I need to say something about the eigenvalues of A. Okay? Now suppose that lambda I is an eigenvalue of A. Okay? That means that these equations are satisfied. AEI should be lambda I EI. A right eigenvector should exist. A left eigenvector should exist. And I know that these equations should also be satisfied, whatever the eigenvalue is. If eigenvalue is real, then this equation should be satisfied. Then this thing is just real. It becomes itself, and this thing is real, and this thing is real. Complex conjugates cancel here. And if eigenvalue is complex, then this equation should still be satisfied. Okay? And remember that an eigenvector should always be a non-zero vector. Okay? Then, so here, let us say that. So let Li be the left eigenvector of A for lambda I. All right? Li is the left eigenvector. This means that it is the right eigenvector for A transpose belonging to lambda I. And here we have Li is the left eigenvector of A. It satisfies this equation as well. The same Li satisfies both of these equations. Okay? We know that by definition, an eigenvector should be a non-zero vector. Okay? So we know that Li is not equal to the zero vector. So here in my proof, because the summation variable here is I instead of lambda I say lambda j. Okay? Then this becomes lambda j, this becomes lambda j, and this becomes Lj. All right? So it's nothing strange here, just change all i's to j because the summation variable is I here, not to confuse it with the eigenvalue index. So now let us multiply both sides. So here I will multiply sigma infinity with Lj from the right, and I will write the sigma infinity with Lj Hermitian from the left. Okay? I will apply this to this equation. So multiply this from the left with Lj Hermitian and Lj Hermitian and Lj. Okay? That is equal to Lj Hermitian a to the n sigma infinity instead of this a to the n transpose, I will write a transpose to the n, and I will write Lj here, plus I will do the same thing to this one, Lj Hermitian, and I would have I from 0 to n minus 1, a to the I, GQG transpose, a to the I transpose times Lj. Okay? Now here, you see that there is powers of A transpose. They are multiplied with the eigenvector Lj. So I have A transpose times Lj is lambda j times Lj. Okay? And here similarly, I have powers of A with the eigenvector Lj complex conjugate. So here I have this type of equation. You see I have A and Lj Hermitian, lambda j complex conjugate, Lj Hermitian here. Okay? So here, in this equation, n is equal to 1. Okay? So in this, what happens when I have n is equal to 2? A square Lj Hermitian is going to be, what is going to be the result here? So I will give a break here, just a little bit, and I will look at this one. A transpose times Lj is, I know that it is lambda j times Lj. What is A transpose square Lj? Lambda j Lj. Those of you who took the course 501, you see everything is related to 501. Linear algebra is an incredible tool that is useful almost everywhere in control theory that you can say, or in signal processing, in telecommunications. It's at almost all parts of electrical engineering. So if you have taken 501, then you would know that if I multiply the square of a matrix with this eigenvector, it is going to give you the square of the eigenvalue times the eigenvector. I'm not going to show it in the long way. Similarly, if I take A transpose to the I, Lj is equal to lambda j to the I and Lj. So similarly, if you have this type of equation, and if you raise A to some power, you just increase the power of the complex conjugate of the eigenvector value here. Okay? So this was my break here. So now let us try to write this. Lj Hermitian sigma infinity Lj is equal to, here this is going to give me, so I have which one? So this one. So Li Hermitian times A to the n is going to give me lambda j complex conjugate to the power n times Lj Hermitian, and this A cancels from here. This is sigma infinity, and this is going to be A transpose disappears, so this happens to be Lj times lambda j to the power n. Okay? And this term is the same. Lj Hermitian, I from 0 to n minus 1, A to the I, GQ G transpose, A to the I transpose times Lj. Okay. So now you see here some scalars. This is scalar, this is scalar, scalar. So I have the lambda j complex conjugate to the power n and lambda j itself to the power n. So this happens to be lambda j conjugate times lambda j to the power n. But that is nothing but lambda j norm square or magnitude square to the power n. Okay, times Lj Hermitian sigma infinity Lj plus I have Lj Hermitian. Unfortunately, I need to write this summation a couple of times more. This is Lj. So I have here Lj Hermitian sigma infinity Lj. So how nice, we have obtained a single quantity here, and we have obtained this one as well, and I'm going to take this quantity to the right, and then I will take the parentheses of 1 minus lambda j magnitude to the power 2n, and Lj Hermitian sigma infinity Lj, that is equal to this quantity, Lj Hermitian I from 0 to n minus 1. This is the last time I'm writing this. G transpose A to the I transpose Lj. So now let us look at what we know. This matrix is positive definite. Okay? This is larger than 0. That means that for non-zero x vectors, this quadratic product is going to be strictly larger than 0. Okay? Lj is non-zero. That since the matrix is positive definite, I know that this quadratic form should be strictly positive. I have already proven that sigma infinity was positive definite, and Lj is non-zero. That means that this quantity, this scalar, should also be positive. Right? This scalar is positive, and this scalar is positive. So I have a positive quantity, which is the multiplication of a positive quantity times something. So I see here that for this type of inequalities to hold, this quantity should be positive as well. Okay? Because if this is 0 or negative, the multiplication cannot be positive. Okay? So that means that this quantity is larger than 0. So here I have 1 minus lambda j to the power 2n is strictly larger than 0. But this is equivalent to lambda j to the power 2n is smaller than 1. But this lambda j is a non-negative quantity, so I can take the 1 over 2n power here, and that gives me lambda j is strictly smaller than 1. Okay. But that means that lambda j is inside the unit circle. What does it mean? Since this is an arbitrary eigenvalue of A is stable. So that completes the proof here. So here we have proven our theorem, and as I told you that in the proof, I have as a side product proven that this sigma infinity should be positive definite. Okay? So here into my theorem I can actually say that if and only if, so I can add here into this statement sigma infinity is a positive definite matrix. Okay? So in addition to the earlier theorem, I have proven this type of theorem as well. So there exists, sigma infinity exists, and it is positive definite. So now let us go into the meaning of this theorem, or the intuitive meaning I would like to talk about a little bit. Remember, reachability was related to controlling the system state by using the input. Okay? So here, this reachability of AS, what might it be related to? Reachability of AS is related to controllability of the state of the system by using the process noise. Okay? So if a system is reachable, then that means that the input can enter all of its modes. Okay? if a system is reachable, that means that by using the input, I can steer the system from any initial state to any final state. That means that the input can enter into all of the modes of the system. Because if the input cannot enter into some modes of the system, then that modes I will not be able to change that modes in the system, and I would not be able to control or steer the state from arbitrary initial conditions to arbitrary final conditions. Okay? So reachability is somehow related to the fact that input entering into all of the modes of the system. Okay? If the input can excite or enter all of the modes of the system, it is reachable, and if the system is reachable, then the input can enter or excite all of the modes of the system. So here we are looking at the reachability of the pair AS, and this S is related to the process noise covariance, GQ-G transpose. So the intuitive meaning of A and S being reachable is the fact that the process noise enters or excites all of the modes of the system. Okay? So reachability of A and S is equivalent to process noise entering into all of the modes of the system, or process noise exciting all of the modes of the system state. So now I will write a statement here. So the meaning of the theorem is nothing but if the process noise enters or excites all of the modes of the system, then stability of A is equivalent to existence of sigma infinity. Okay? If and only if means the equivalence between A is stable, A being stable, and sigma infinity existing. Okay? If instead of AS being reachable, I can say that if the process noise excites or enters all of the modes of the system, then stability of A is equivalent to existence of sigma infinity. In order to illustrate this intuitive meaning, I will go back to the example that we have seen in the previous lecture. So we have seen an example where A was given like this, xk, and I would have process noise in this manner. In this case, you see that A is not stable, but we have actually seen that sigma infinity was given to us as 1 and 4 over 3. Okay? Was it like this? Yes, that's correct. So in this case, I see that, and here A is not stable. Sorry. So you see that we don't have the equivalence of stability of A and sigma infinity existing. Sigma infinity exists, but A is not stable. So definitely this theorem cannot hold. Okay? What does it mean? Conditions of this theorem should not be satisfied by this example. In this case here, WK was normal 0, 0, 1, I think. Sorry, I do not want to make any mistake here. Yes, WK was 0, 1, so Q is 1 in this case. And what is GQ G transpose? GQ G transpose is nothing but I would have this matrix 0, 1 times 1 times G transpose, which is given like this. But here you see that I can actually separate this 1 into this 0, 1, 1 times 1, 0, 1. Okay? So you see here that I can define this matrix as S, and I can define this matrix as S transpose. Okay? So one square root here that I can define is just 0, 1 times 1. If this was just another number, like let us say 9, then I would separate it into 3 and 3. Then S would be 3 times this vector, and you see that its transpose is here. So one square root of that matrix GQ G transpose would be the vector just 0, 1. So here one square root S is 0, 1. Now I want to check the reachability of this with this A. 1, 0.5, 0, 0. Okay? So this is the reachability matrix is going to be S and AS, and that is going to be 0, 1 and 0, 0.5. Okay? You see that one of the rows is just equal to 0, so this is not full row rank. Not full row rank, meaning that AS is not reachable. Okay? Meaning that this theorem does not hold for this example. What does it mean? The stability of A is not equivalent to the existence of sigma infinity, and actually we see that. So sigma infinity existing does not imply the stability. Sigma infinity exists, but A is not stable here. Okay? So why is that? Why is this not reachable? Let us write the equations of the system. xk plus 1, 1 is equal to xk1. The modes are independent, and I have no process noise in the first state variable. And in the second state variable, xk plus 1, 2 is equal to 0.5 xk sorry, I'm making too much mistake, plus wk. So you see that the process noise does not excite this mode of the system. Okay? The first state variable is not excited by the process noise. That is why this system this AS is not reachable. Or because AS is not reachable, the process noise is not exciting some modes of the system. Okay? So I might have other types of non-reachability here. This can be 1, 1, and this can be 1, 1, and I would have just another type of non-reachability in such a case. In that case, the process noise would not actually excite, again, some modes of the system, some linear combination of the states here. But here we see it quite easily for this example that the process noise is not exciting one of the modes of the system. And you see that here, whatever the initial covariance of this first state variable, it's going to remain the same because the first state variable is not changing. So that means that the initial uncertainty of this first state variable will be the final uncertainty of this first state variable, because the variable really does not change. It's always going to be equal to the its initial value. And the initial uncertainty here for this system was I2. Sigma 0 was I2 here, meaning that 1, 1, 0, 0. And we see that the initial variance of the first state variable was 1, and the final variance of the first state variable is 1. This is really not surprising, because the first state variable really does not change as I increase k. All right? So we see that uncertainty neither decreases nor increases. It just remains the same as time progresses. All right? And since process noise really does not excite this system, it does not excite this mode, even if this mode of the system is unstable, because it is as you see, there is a 1 here corresponding to the eigenvalue 1 on the unit circle. This mode of the system is unstable because it has an eigenvalue 1, and the process noise, the variance can remain constant because the process noise does not excite this mode. Okay, the uncertainty here remains bounded, and it is actually constant here because this mode is unstable, but it's not excited by the process noise. What can I change in the system to satisfy the reachability criterion? Now consider the system xk plus 1 is equal to 1, 0.5, 0, 0, xk. Let me say both of these are 1. In this case, the system is going to be reachable. Okay? Why is that? Because S is, let us look at S in this case. GQ G transpose is going to be, I have 1, 1, 1, 1, 1. But you see that here, this is going to be my S. S is going to be 1, 1. And if I look at the reachability matrix, M is equal to S, AS. And in that case, I would have 1, 1 and 1, 0.5. And you see that the rows of this matrix are all linearly independent, so full row rank. But in this case, I can also say that here the determinant is just non-zero, meaning that this matrix is invertible, so we have reachable system. Reachable A and S. So that means that in this case, stability of A is equivalent to the existence of sigma infinity. Okay? So if sigma infinity does not exist, then I can say that A is not stable, and if A is not stable, sigma infinity will not exist. Okay? In this case, is this A stable? It's the same A, so this is unstable. So I know that in this case, sigma infinity is going to not exist. Sigma infinity is not going to exist. So it is either going to go to infinity or it's going to oscillate. It's not going to converge anywhere. That is what does not exist mean. But here it's really easy to say, it's easy to see why it does not exist. Let us look at the first state vector, first state variable. Xk plus 1, 1 is equal to xk1 plus wk. Okay? In this case, you see that the process noise enters also into the first state variable. Okay? But here I can actually write this as x11 is equal to x01 plus w0. So x21 is equal to x11 plus w1, but x11 is x01 plus w0 plus w0 plus w1. So you see the trend. This is a random walk type of model. If you have taken the stochastic processes course, you might have heard about the name random walk. So this is a process that is called random walk. It remains constant except for the addition of a noise. So we are always adding an additional noise term to the initial condition. So I can write here xk1 is equal to x01, the initial condition, plus I from 0 to I have k minus 1, wi. So now what is the variance of this thing? So here the initial variance of the first state variable is 1. And the variances of the process noises are also 1. Here, I sum k independent noise terms with variance 1. That means that variance of xk1 is actually going to be here k. Summation of the variances, which would be k. So you see that when I let k go to infinity, the variance of the first state variable is going to diverge. It's going to go to infinity. So this sigma infinity covariance is going to have an infinity here, which means it does not exist. All right? Why does it happen? Because A is not stable. Okay? If A was stable, then I would have seen that sigma infinity would exist. But because A is not stable, and since we have reachability here, we will not have the existence of sigma infinity anymore. And that is happening, as you see, as soon as the process noise excites all of the modes of the system. Okay? So here, you can actually guess what would happen if I change this number to 0.9, for example. In that case, the A matrix would be stable, and the system would still be reachable. And in that case, you would see that sigma infinity would exist. Okay? So here, just as an exercise, try to replace this one with 0.9 and then repeat this example. Okay? Try to see. So here I see that limit variance xk1 goes to infinity. It does not exist. Replace this with 0.9 and repeat this example. Find the final covariance. In that case, the system is going to be reachable. AS is going to be reachable, and sigma infinity will exist. And you can also you can also try other type of systems. So as you see, this concept was quite complicated, and you would need to understand many concepts from many areas. Linear algebra being one of the most important ones, but as you see here, we are using some concepts from stochastic processes as well. So I have tried to explain this reachability concept as much as possible that can be reasonable in this course. I'm not assuming that you have taken a linear system theory course. That is why I made that type of explanation. So I hope it is useful at this time. But this finishes this lecture. So we are almost about to finish the third chapter in the book. There is only one subsection that is remaining, and that is going to be Gauss-Markov processes, which is going to be quite interesting. We are going to assume that a stochastic process is both Gauss-Markov. For example, this type of example with white process noise and independent basic variables would be a Gauss-Markov, white and Gauss-Markov process when everything is Gaussian. We're going to see also another property, and that is going to be the property that if we are given a Gauss-Markov process, we will be able to extract a state space representation for it in this form. Actually, we will be able to define process noise and A matrices, etc., given any Gauss-Markov process. But that's going to have to remain for the next week. That's all for this week. Thank you very much for watching. Bye.